Welcome everyone! In this lesson, we are going to explore the fascinating world of solving algebraic equations numerically, a process often referred to as root finding. Many equations encountered in science, engineering, and mathematics, especially complex ones, do not have solutions that can be written down in a simple, closed form. This is where numerical methods come to our rescue, providing powerful techniques to approximate these elusive roots. Our main purpose today is to understand and implement some of these numerical root-finding techniques using Python. We will begin by looking at a specialized method for polynomials available in the NumPy library, specifically the numpy.roots function. Then, we will move on to a more general approach using the SciPy library, with the solve function, which can handle a broader class of equations, including transcendental ones. Throughout this session, we will emphasize not just how to use these tools, but also why they work, their limitations, and how to interpret the results, often using visualizations to build our intuition. By the end of this lesson, you will be able to numerically find roots for various types of equations, and appreciate the practical power of these computational methods. We often encounter equations where finding an exact solution is challenging. For instance, consider the polynomial equation f of x equals x to the power of 5 minus x plus 1. While the intermediate value theorem assures us that if a continuous function changes sign over an interval, it must have a root within that interval, this theorem does not tell us how to find that root explicitly. For many polynomials of degree 5 or higher, like this one, there is no general algebraic formula to express the roots. So, we turn to numerical approximation. The core idea is to find a value of x. Let us call it x subscript r, such that the function's value, f of x subscript r, is very close to 0. We define this closeness using a small positive number called tolerance, often represented by the Greek letter epsilon. If the absolute value of f of x subscript r is less than this tolerance, say 10 to the power of -6, we consider x subscript r a sufficiently good approximation of the actual root. To get a better feel for the function we just discussed, x to the power of 5 minus x plus 1, this code block helps us visualize it. First, it imports the necessary libraries, matplotlib for plotting and numpy for numerical operations, especially for creating an array of x values. A Python function f is defined to represent our polynomial. Then, a range of x values is generated using numpy's arrange function, covering an interval where we expect to see interesting behavior, in this case, from -1.5 to 0. The pltplot command then draws the graph of our function over this range. To make it easier to see where the roots might be, a horizontal dashed line is added at y equals 0, representing the x-axis. The resulting plot, titled to indicate the function, will show us how the function behaves and where it appears to intersect the x-axis, giving us a visual hint about the location of its real root. It is important to understand a detail about how matplotlib interacts with numpy arrays versus standard Python lists, especially when plotting functions that perform array operations. The plotting command pltplot xrange fxrange works smoothly when xrange is a numpy array because our function f, which uses x times asterisk 5 feet, can operate element-wise on the entire array efficiently. However, if xrange were a plain Python list, applying such a numpy-optimized function directly might not work as expected or could lead to errors. This code snippet demonstrates this point. It first converts the numpy array xrange into a Python list and prints its type to confirm. Then, it attempts to plot fxrange using this list. You would typically find that this either raises an error or does not produce the intended plot because the function f is designed for array inputs, not lists, when vectorized operations are involved. Following up on the previous point, This code snippet shows the correct way to handle the data for plotting with functions designed for NumPy arrays. We start by converting our xRange variable, which was turned into a list in the previous step, back into a NumPy array using np-array. We then print its type to confirm the conversion. After ensuring xRange is indeed a NumPy array, we can successfully call our function f with xRange as fxrange. The pltplot command will now work as intended, correctly plotting the function because both the input xRange and the output of fxrange are compatible NumPy arrays. This reinforces the importance of using NumPy arrays when leveraging the power of vectorized computations within NumPy and plotting libraries like matplotlib. For the specific task of finding roots of polynomial functions, NumPy provides a very convenient tool called numpy.roots. This function is designed exclusively for polynomials. To use it, you need to provide the coefficients of the polynomial. These coefficients must be given in a sequence, typically a list or a NumPy array, ordered from the coefficient of the highest power term down to the constant term. For a general polynomial, say c subscript n times x to the power of n plus c subscript n minus 1 times x to the power of n minus 1 and so on, down to c subscript 1 times x plus c subscript 0, the input to numpy.roots would be a list like open bracket cn, cn minus 1, c1, c0 close bracket. It is crucial to remember that numpy.roots is specialized for polynomials. It may not correctly find roots for non-polynomial functions, such as transcendental functions involving trigonometric or exponential terms. Let us consider a concrete example to understand how to use numpy.roots. Suppose we want to find the roots of the quadratic polynomial f of x equals 4 times x squared plus x minus 66. This is a polynomial of order 2. To use numpy.roots, we first need to identify its coefficients. The coefficient of x squared, which is c subscript 2, is 4. The coefficient of x, which is c subscript 1, is 1. And the constant term, c subscript 0, is negative 66. These coefficients are then arranged into a list in descending order of power. Arranged by equals open bracket 4, 1, negative 66 close bracket. This list arranged by is then passed as an argument to the numpy.roots function. The function will then compute and return the approximate values of the roots for this specific polynomial. Now, let us apply what we have learned to actually solve for the roots of the polynomial f of x equals 4 x squared plus x minus 66 using numpy.roots. The code begins by importing the NumPy library, which is essential for using numpy.roots. Then, a list named coefs is created, containing the coefficients of our polynomial, 4, 1, and negative 66, in that specific order. The numpy.roots function is then called with this coefs list, and the results, which are the roots of the polynomial, are stored in a variable called roots. Finally, these roots are sorted using np-sort and printed. As suggested, it is always a good practice to plot the function and its roots to visually verify if the solutions obtained are reasonable and make sense in the context of the function's graph. This code block focuses on visualizing the roots we just found for the polynomial 4x squared plus x minus 66. First, it imports NumPy and Matplotlib's pyplot. It defines our polynomial function, making it easy to calculate k-phi values for given x values. The code also shows an alternative way to evaluate polynomials using np.polyval, which takes coefficients and x values. After obtaining the roots using numpy.roots as before, it extracts their real parts and rounds them for cleaner presentation. The core of this snippet is the plotting. It generates a range of x values around the roots, plots the polynomial function as a curve, and then uses PLT scatter to place distinct red x markers at the locations of the calculated roots on the plot. A horizontal orange dashed line at y equals 0 is added to clearly indicate the x-axis, and a legend helps identify the plotted roots. This visual check is invaluable for confirming that our numerically found roots indeed correspond to where the function crosses the x-axis. An important observation for the polynomial f of x equals 4x squared plus x minus 66, which we just analyzed and plotted, is that both of its roots are real numbers. When we solved for the roots using numpy.roots and then plotted them, we saw two distinct points where the parabola intersected the x-axis. This indicates that there are two real solutions to the equation. 4x squared plus x minus 66 equals 0. This is not always the case for all polynomials. Some can have complex roots, which would not appear as x-intercepts on a standard plot of f of x versus real x. Let us try an exercise to solidify our understanding of how polynomial coefficients are represented. If a programmer writes coefs equals open bracket 0.5, negative 0.7, negative 5.1, 0, 0, 7.0 close bracket, and then calls numpy.roots coefs, what polynomial are they trying to solve? Remember, the coefficients are listed from the highest power downwards. Since there are 6 coefficients, the polynomial is of degree 5. So the polynomial is 0.5 times x to the power of 5, minus 0.7 times x to the power of 4, minus 5.1 times x to the power of 3, plus 0 times x to the power of 2, plus 0 times x to the power of 1, plus 7.0. The subsequent code block then takes these exact coefficients, uses numpy.roots to find all the roots of this fifth-order polynomial, sorts them, and prints them out for us to inspect. Looking at the roots calculated for the polynomial f of x equals 0.5x to the power of 5, minus 0.7x to the power of 4, minus 5.1x to the power of 3, plus 7.0, we can make an important observation. Unlike the previous quadratic example where both roots were real, for this fifth-order polynomial, not all of the roots are purely real numbers. Polynomials of degree higher than 2 can, and often do, have complex roots, which occur in conjugate pairs if the polynomial coefficients are real. The output from numpy.roots will include these complex roots, and it is something we need to be aware of when interpreting the results, especially if we are only interested in real solutions where the function crosses the x-axis. The task now is to visualize the roots we found for the polynomial 0.5x to the power of 5 minus 0.7x to the power of 4 minus 5.1x to the power of 3 plus 7.0. This code aims to plot the function and mark all the roots returned by numpy.roots. It starts by defining the coefficients and calculating the roots, then sorts them. A helper function, polynomial underscore function, using NP polyval, is defined for easy evaluation of the polynomial. The code then generates a range of x values between the smallest and largest real parts of the roots to plot the function. Finally, it plots the polynomial curve and uses PLT scatter to mark all the roots. It is important to observe what happens when plotting these roots, as some of them are complex. Matplotlib's scatter function, when given complex numbers for coordinates, will typically issue a warning and plot only their real components if the UE values are real, or plot them in the complex plane if configured to do so. But here we are plotting f root, which might be complex for complex roots. If you look closely at the plot generated by the previous code, you might notice something interesting. For our fifth-order polynomial, numpy.roots finds 5 roots, as expected from the fundamental theorem of algebra. However, not all of these are real roots. The plot might seem to show markers for all roots along the x-axis, or close to it. This can be misleading, because complex roots do not correspond to x-intercepts in a plot of f of x versus real x. If the imaginary part of a complex root is 0, it is a real root. If it is non-zero, it is truly complex. The code here demonstrates how to filter out these non-real roots. It iterates through the list of roots, and for each root, it uses numpy.isReal to check if it is a real number. If it is, numpy.real is used to extract its real part, which is then added to a new array called real roots. This way, we get a list containing only the actual real roots of the polynomial, and we also evaluate the polynomial at these real roots to ensure they are indeed close to 0. Now that we have a way to filter out only the real roots, this code block demonstrates how to create a more accurate plot. It uses the real roots array, which contains only the genuine real solutions to our polynomial equation. An appropriate x range is determined based on these real roots to ensure they are well displayed. The polynomial function is plotted as a curve over this range. PLT scatter is used again, but this time it only marks the positions of these filtered real roots on the graph. A horizontal line at y equals 0 is also drawn for reference. This corrected plot accurately shows where the polynomial function intersects the x-axis, providing a clear visual representation of its real roots without the potential confusion from complex roots. This section presents a comprehensive exercise. The goal is to write a piece of Python code that can take the coefficients of an arbitrary order, n polynomial, and perform a full analysis. This involves using numpy.roots to find all its roots, both real and imaginary. The code should then print out all these roots. Furthermore, it needs to automatically count how many of these roots are real and display their values. Finally, it should generate a plot of the polynomial function, clearly indicating the positions of its real roots on the graph. The provided sample code implements this. It defines a list of coefficients for a test polynomial, calculates all roots, filters to find the real roots, prints the total list of roots, and the filtered real roots along with their count. It then defines the polynomial function for plotting, and visualizes both the function and its real roots. You are encouraged to test this code with different polynomials, like x to the power of 5 minus x plus 1, or x to the power of 5 minus 2, x to the power of 4 minus x to the power of 3 minus x plus 1, to ensure its robustness. We now transition to a more general method for finding roots, which is not limited to polynomials. The scipy.optimize module offers a function called solve, which can find roots for a wide variety of functions, including those that are non-polynomial or transcendental. A key characteristic of solve is that it is an iterative solver, meaning it starts with an initial guess for the root and tries to refine it until it converges to an actual root. Therefore, you must provide an initial guess to solve. Typically, solve finds one root at a time, usually the one closest to your initial guess. If a function has multiple roots, you will need to try different initial guesses to find them. The code here demonstrates this by defining two different functions, f1 of x and f2 of x. For each function, it calls solve twice, with different initial guesses, chelvin1 and chelvin2, attempting to find roots. The results, along with the function values at these points, are printed, and both functions and their found roots are plotted. Let us carefully examine the results from using solve in the previous example. For the first function, f1 of x, which was x to the power of 5 minus x plus 1, you might observe that one initial guess, perhaps 12(1), led solve to a valid root. However, the other initial guess, 12(2), might have resulted in solve converging to the same root, or perhaps to a value that is not a root, or it might have failed to converge. For the second function, f2 of x, it is possible that both initial guesses successfully located distinct roots. This behavior highlights a critical aspect of using solve. The solution it provides is highly dependent on the quality of the initial guess. If the guess is too far from an actual root, solve may fail or find an unintended solution. Therefore, it is always essential to choose initial guesses thoughtfully, perhaps by first plotting the function to get an idea of where roots might lie, and to rigorously check whether the answers obtained from solve are indeed correct roots by substituting them back into the function. Now let us apply solve to find the roots of a transcendental equation, which is an equation involving functions like trigonometric, exponential, or logarithmic functions. Our example is to solve x times cosine of x equals 4. To use solve, we first need to rewrite this as f of x equals 0, so our function becomes f of x equals x times cosine of x minus 4. The provided code defines this function f. Then it calls solve twice, each time with a different initial guess. For instance, one guess is 10.0, 1, and another is negative 1.0, 2. The roots found from these guesses, r1 and r2, are printed along with the function values f of r1 and f of r2 to check if they are close to 0. Finally, the code plots the function f of x and marks the positions of the found roots r1 and r2 with red scatter points, allowing for a visual verification of the solutions. Consider the function f of x equals x times cosine of x minus 4 again. It is known that transcendental functions like this can have infinitely many roots. The question posed here is specifically about the interval where x is between -18 and -6. It suggests there might be a total of 4 roots in this particular range. How would you go about finding all of them using solve? Since solve typically finds one root at a time based on an initial guess, you would need a strategy. Sample code demonstrates finding 2 roots within this broader interval by providing 2 specific initial guesses, -18.0 and -14.0. These guesses lead to the roots r1 and r2. The plot then shows the function and these 2 found roots. To find other potential roots in this interval, you would need to try additional, carefully chosen initial guesses within or near the specified range, perhaps by examining a plot of the function over this interval to estimate their locations. In this lesson, we have explored powerful numerical techniques for finding the roots of equations. We began with numpy.roots, an efficient method tailored specifically for polynomial equations, which finds all roots, both real and complex, given the polynomial's coefficients. We learned the importance of correctly interpreting its output and visualizing the real roots. We then moved to scipy.optimize.fsolve, a more versatile tool that can tackle a wider array of functions, including non-polynomial and transcendental ones. The key takeaway for solve is its reliance on an initial guess and its nature of typically finding one root at a time. This highlighted the need for careful selection of these guesses, often guided by plotting the function, and the necessity of verifying the solutions. These numerical methods are indispensable when analytical solutions are out of reach, enabling us to solve complex real-world problems. The final exercise encourages you to think about strategies for systematically finding multiple roots using solve, reinforcing the idea that thoughtful application of these tools is crucial.